Okay, so I think we should start. It's 11:30. So the next presentation is Evie van Wimbroek, influence of the welding process on the residual welding stresses in an orthotropic steel bridge deck. Please.
Good morning, everybody. My name is Evie van Wimbroek. I am a PhD researcher at the Civil Engineering Department at Ghent University in Belgium. And today I will present to you my paper about the influence of the welding process on the residual welding stresses in an orthotropic steel bridge deck. Large steel bridges require a lot of complex welding operations. As you can see here, this is a steel tubular arch bridge, and that has a lot of complex welded nodes. For example, here a welded K node. Also for orthotropic steel bridges, which is the main topic for today, you can see that over here. Also here a lot of welding operations are present. The longitudinal stiffeners are welded to the deck plate, and also weld connection is present with the transversal beams. Residual welding stresses are introduced due to the welding and due to local plastic deformation. These welding stresses can have a large impact on the fatigue strength. We have to avoid tensile residual stresses to be present, since they tend to open cracks and they increase the crack rate propagation. In order to have an idea about the residual stress distribution for an orthotropic steel deck, we made a three-dimensional finite element model which simulates the welding procedure. We investigated the weld connection of longitudinal stiffener to the deck plate. We performed decoupled thermal mechanical analysis. During the thermal analysis, you can see over here, this is the temperatures which are introduced during the welding. And these temperatures are used as a time-dependent load for the mechanical analysis in order to determine the residual stresses. We are going to look at the welding process and the parameters used during this process. We will see a variation of the size of the tack welds, the welding current, and the welding speed in order to obtain the most optimal welding procedure, which leads to the minimal amount of tensile residual stresses. The geometry that we looked at was the longest stiffener to deck plate weld, as you can see here. We have a weld throat of 7 millimeters, and the longitudinal stiffeners have a closed trapezoidal shape. The steel which was used was structural steel with a yield strength of 235 megapascals. The length which was taken into account for the simulation, that is 250 millimeters. This is equal to the distance between two subsequent tack welds. Now for the welding procedure, first the orthotropic steel deck is inverted, and the longitudinal stiffeners are put in the right position on the deck plates with some tack welds. These prevent local distortion during the welding, and they obtain the good position on the deck plates. And then twin wire submerged arc welding is used, and this is that along both sides simultaneously the stiffener is welded to the deck plate. This is done from the exterior of the stiffener, so we have to make sure that a decent weld melt-through is obtained. For this welding procedure, we are going to look at different configurations and a variation in the size of the tack welds, the welding currents, and the welding speed. So we made a finite element model with the software Siemens NX with Samsung solver. We performed a decoupled thermal mechanical analysis. This means that the deformations are dependent on the temperature, but the temperatures are independent on deformation. For the thermal analysis, we put a heat flux on the model, and we calculate the time-dependent temperatures, and these are used during the mechanical analysis to calculate residual stresses. We made use of three-dimensional 8-node brick elements. These are linear brick elements since they are the best option for plasticity, and due to the high temperatures from the welding, plasticity will occur. So this is an image of the thermal analysis. So we put heat flux on the model, and these heat flux can be determined based on the heat input model of Goldak. This has a double ellipsoidal heat source model, and the parameters for these models can be determined based on the weld geometry. Also, thermal material properties will be specified. These are the thermal conductivity and specific heat in function of the high temperatures which will arise during the welding. And for the boundary conditions, these are used to the heat interference, the convection and emissivity are specified here. During the thermal analysis, the mesh of the deck and the stiffener are not yet connected. Only after passage of the welding torch, this is after the temperature of 1440 degrees Celsius is reached. This is here. You can see that the weld melt-through is obtained and that we have a good connection of the deck plate and the stiffener. And only after this time in the model, also the meshes will be connected. And for the structural analysis, here these temperatures are introduced as a time-dependent loads. And for the boundary conditions, we have the tack welds. We have the tack welds here and here. This is the middle, here and here. These are the welding lines. And for the deck plate, we simulated it as a rigid surface by means of a series of strings. These are the results of the residual stresses in the transverse direction. This is the direction which is perpendicular to the welding line. And this is the final time step. So after cooling down, after the welding, you can see that here there are tensile yield stresses present. In the middle, we have a compressive residual stress about 45 megapascals, and near the sides, the residual stress is close to zero. We always look at the middle section for the results in order to avoid any interference of the boundary conditions. Now we have this residual stress distribution from our reference model, but we want to see whether we can reduce the tensile residual stress zone in order to prevent that the cracks will open faster. So we did some variation of different parameters, and the first one was the size of the tack welds. We saw that this parameter has no influence on the residual stresses. The residual stress was exactly the same for the three different tack weld sizes that we used. Also, for the welding current, we saw that lower welding current than the reference model had no effect on residual stress. However, a higher welding current, higher than 780 amperes, will result in lower residual stresses and a smaller tensile yield zone. So here you see that the tensile yield zone is a little bit smaller, and this is what we want. The parameter which had the most influence was the welding speed. The higher the welding speed, the smaller the residual stresses, and especially the tensile yield zone was really smaller when the welding speed was higher. So in this way, we can optimize our welding process. The size of the tack welds has no influence. We have to make sure that the welding current is higher than that from our reference model, and the welding speed is increased in the way that it is possible. This leads to an optimized welding process, which leads to smaller tensile residual stresses. Here we can see a figure of the crack rate propagation from our model. but this is without the inclusion of the residual stresses. So this is when we take the most severe residual stress distribution, and now in future we can optimize this image by implementing a residual stress distribution with more optimal residual stresses, so smaller tensile residual stresses, in order to reduce the crack rate propagation and the crack growth where possible. This was it. I'll thank you for your attention.
Thank you very much. Again, for other people to, if they want to attend, it will be better to have a break of 4 minutes.